Question 4. Acrylonitrile, acrylonitrile can be used as start material for synthesis of butane 1,4-diamine, as shown in this reaction scheme. Use IUPAC names to rule isomer W. Isomer W, it's got 1 carbon, 2 carbon, 3 carbons. It's going to be propane. The bromo is on the 3rd carbon, so 3 bromo, propane, and this carbon comes from nitrile group, so it's going to be 3 bromo propane, 3 bromo propane nitrile, 3 bromo propane nitrile. Usually when they ask you to name an isomer, it's got one trick, or naming using IUPAC rules, it's got a trick or something, because it's not going to be a simple mark for 1 mark. Not going to be a simple thing. Reaction 1, produce a mixture of W and the 2 of the isomers. Draw the structures of the 2 of the isomers, and then explain by considering the mechanism of reaction where all 3 isomers are found. So, stage 1, the types of isomers found. Stage 1, types of isomers found. Well, we've got CH3, CHBrCN, CH3, CHBrCN, and they exist as 2 optical isomers, aka exists as 2 optical isomers, aka enantiomers. You could say it exists as 2 enantiomers. Stage 2, the mechanism. Mechanism. So, how do we form isomer W? Well, we've got this reaction with a hydrogen halide, hydrogen bromide, to form 3 bromo propane nitrile. So C11C HCN H, and what happens is the hydrogen bromide, hydrogen is partially positive, bromine is partially negative, from the double bond to the hydrogen, and then from middle of the H to the Br. And what you form is you form this. And a plus charge here. Actually, the hydrogen's here and the Cn is here. With the plus charge here, because we know that because here the Cn is always here for a reaction at the end of reaction 1 and the end of reaction 2. So we form this where the carbon is positive, and this is secondary carbocation. The intermediate structure is secondary carbocation. Secondary carbocation. That should be a H. And then we can also form a primary carbocation, where all that happens is Cn is still here, H is still here. Now the H is here and the positive charge is here. So what will happen is that the Br with the lone pair of electrons negative will bond here instead, and that's primary carbocation. primary carbocation. Primary carbocation. The carbocation is an organic ion containing a positive charged carbon atom, and this is the intermediate structures. Now for stage 3, where all 3 isomers are found, go through the well, that's what I talked about previously. It exists as 2 optical isomers. Let's explain that in stage 3. If I have enough space, I'm just going to have to do it here instead. But in the exam, please answer the question in the line given to you. Otherwise, I'm not sure, but they might not give you the mark. Probably won't, because it is A-levels after all. It's not just a test, it's A-levels. You got GCSEs and then whoop, you got A-levels. So they're going to take it seriously, and they probably won't allow you to write just on the questions next to it. You have to show the answers on the lines, I'm pretty sure. So the 2-bromo isomer, yeah, two-bromo isomer has a chiral carbon. Chiral carbon. And what is a chiral carbon? Well, you definitely do need to know this. A carbon atom that has 4 different groups attached to it. So it's a chiral carbon that has 4 different groups attached to it. And then the next point we want to talk about optical, because the secondary carbon positive is planar. Optical because secondary C plus optical because secondary C plus planar, so can be attacked from above or below. That's really key. So can be attacked from above or below, and hence optical. So it can be attacked. Let's actually show it. What is it? CH3 HCN. Yeah, there's CH3 CHCN. So let's just draw it here. The idea, what I'm trying to explain is, you got the CH3. You've got the CN. You've got the hydrogen, and then now you have the Br minus here with the lone pair of electrons, and the Br minus here with the lone pair of electrons. The carbon is positive. We know optical because the secondary C plus carbon positive is planar. It's a flat shape, so it can be attacked here below, or it can be attacked above. And that's really it for the optical isomerism part. Tricky 6 marker. Very tricky 6 marker. I feel like the part that will trick students out is considering the mechanism of the reaction. It actually wants you to show where the curly arrows go, and then show the intermediate structures of primary carbocation and secondary carbocation. And then the rest of it, yes, optical isomerism or 2-bromo isomer, 2-bromo isomer has a chiral carbon, 4 different groups, hence non-superimposable mirror images, and optical because secondary C plus planar, so it can be attacked from above or below. And then stage 1 is just a type of isomers found. CH3, CHBrCN exists as two optical isomers slash enantiomers. And that's really it. We could also show this idea of the chiral carbon. So the carbon CH3 CN, that should be CN, Br is attached to 4 different groups, or it could be in optical isomerism CCH3, this in this way instead of CN and C, Br here, and the hydrogen here. So we basically, like a mirror image. So CH3, and then the other way, CH3 stays the same, but the CN in this case flips over to NC, this H flips over to H, and the Br flips over just to the left hand side. And then 4.3, identify the region that was warmed with the isomer W in reaction 2. Reaction 2, so what are we going from? We're going from BRCN to NCCN. It's going to be KCN. And the other reaction condition, aqueous and ethanol. State the region and reaction conditions needed for reaction 3. Reaction 3 is going to be hydrogen gas, H2, and Ni. And the equation, well, we've got N C CH2 CH2CN. So this, so N C CH2 CH2CN. And what we're adding, a hydrogen gas, and we're forming, well, we already know what we're forming. We just need to show the addition of the hydrogen gas, H2N CH24, and yeah, it should be all be one. I'm sure it down, but you get the point. NH2. Now we need to balance it. Is it balanced? No. How many hydrogens here? 2, 4. How many hydrogens are formed? 2, 4 plus another 8, because you got a 4 here. So 2 times 4 is 8. So we need a 4 here, the hydrogen gas, to balance it out. And that's it. 4.5, an incomplete equation for the formation of nylon 4,6 from 5 molecules of butane, 1,4-diamine, and 5 molecules of hexane dioic acid is shown. Deduce the values of x and y in this equation. Okay. X is gonna be 5. X is gonna be 5. Y is gonna be 9. So 9 H12, 9 water molecules. Not much to that. You can try counting out, balancing it, etc. etc. Figure 6 shows a section of the nylon 4,6 polymer molecule. Remember, nylon is on the specification. Obviously, otherwise it probably wouldn't be mentioned it. Drawn figure 6, another section of nylon 4,6 polymer showing 2 hydrogen bonds between the sections. Between the 2 sections. So we've got HN, CH2, so we've got C double bond O, H2C, C double bond O, HN, CH24, NH, there, okay? And what we're just going to do now is we're just going to draw it again. But we want the hydrogens and the oxygens to basically align with each other, which is going to be hard to do here because I'm drawing it so big, but on the paper it should be definitely slightly easier. Now we've got H2C4, yeah, we've got H2C4, C double bond O. Okay, but the idea is the oxygen has a lone pair of electrons, and just show a bunch of dashes to the hydrogen and a bunch of dashes to the hydrogen. It should be in a straight line, like I said, but obviously I can't draw this to a smaller scale, that's why. And that's the hydrogen bonding. And the oxygen lone pair and the electron deficient HNOF atom, in this case hydrogen. And that is the end of question 4.